先生，下午好，早上好. I don't know what it is actually. Still morning. How you doing?
Yeah, I'm doing great. How are you?
Yeah, good. We're having a lot of fun.
Nice, nice.
It's interesting. It's um it's surprisingly productive to combine architects and planners in and shake really hard to see what happens.
It's
The thinking is so different that's completely it's complementary rather than
yeah,
competing. It's very interesting.
awesome.
Yeah, it's been good. They're literally here in the room as well. We're quite a big group. Some people joining online as well. But that does mean I will kind of ask them to turn off sound and et cetera, et cetera. One second. I hope technically that it does echo because 30 computers in one room and everybody's got their
I think I would suggest everyone to turn off the camera. So it's probably going to help with the internet.
yeah, absolutely. Oh, I should have taken a screenshot, but okay. That's okay. That's okay. Is Khalil here? Not yet. Still waiting for one important person. Let me do the introduction first, very, very briefly. So for this work, we super quiet. All right. Yes, there we go. Still can hear an echo, but maybe if I stop talking, it's going to be easier. There we go. Welcome again. We've met. Maybe I take a step back. I was fortunate enough a few weeks ago to meet Professor Liu or Liu Pengyuan in Shanghai, where they run a similar but much more sophisticated workshop that introduced artificial intelligence, machine learning as a way of dealing with these complex network and complex data problems for the urban environment. Professor Liu is a lecturer in digital planning, urban analytics subject group that's part of the Urban Studies and Social Policies Division at the University of Glasgow. Today is specifically for our Undip cohort, who are quite advanced in data-driven modeling. And for me, because I missed your talk last time, and I'm absolutely honored and honest about the fact that it's a pleasure to have this here now tonight in Bali again. I hope that is a sufficient introduction. I will turn my sound off now, and then the stage is yours.
Thank you. Thank you so much for the kind introduction. Let me share my screen. All right, I hope you can see my screen. Yeah. All right, fantastic. Thank you so much again for your invite for me to join in this wonderful workshop. And today I'm going to talk a little bit about AI. And I know you are doing something with networks. So actually, my topic today is about graph modeling and spatial explicit GeoAI in urban analytics. A brief introduction of myself. I am Prof Liu, and I am currently a lecturer in digital planning at the University of Glasgow. But I had various experiences as postdoc, in Singapore and also in Finland, Europe. I come from a computer science background, and then joining the Department of Geography as a PhD, and I got my PhD degree at the University of Leicester for geography. But since I come from computer science background, all the things I saw about urban geography or planning perspective kind of project are all from a methodologist kind of site. So I call myself a methodologist because I love programming and I love to say how the programming can help us to develop better cities per se. Um, so I'm not sure how much of you have the sort of like AI background or quantitative geography background, but I think I would just give a thorough kind of introduction about this kind of topic. I mean, cities used to be designed and planned on the intuitions, such as we have early kind of urban planning concept of radiant cities or garden cities or zoning laws from early 20th centuries. All those kind of urban planning kind of philosophies based on the intuition of the planners, meaning that the planners gave their kind of thought about which areas in the city will be designed into what district or whatever, right? But nowadays, given the more and more advanced technologies being developed, I would say our cities nowadays are planned based on the evidence. In terms of evidence, we are talking about, for example, a well-known concept is a 15-minute cities, right? It relies on the GIS-based accessibility metrics in order to assess whether our cities is walkable enough. And in a more advanced kind of manner, in China, the digital twin cities is becoming such a trending topic, not only in China, but also, to be honest, like worldwide. And in Shanghai, they're trying to taking a step even forward. They're trying to build this kind of concept of quantum cities, which is even a step forward based on digital twin city. But even given all this kind of, I call it buzzword, all this kind of technology heavy kind of city planning or city governance kind of process will be based on the evidence and also the data and also technologies. So to begin with, I would say that most of us know that cities are complex systems. As every single report or the paper says about the cities, that over 60% of world's population will be living in the urban areas. So with the population fluctuating into the urban areas, urban science nowadays is undoubtedly a science, and every day we create a huge number of data based on our everyday lives. And on the left side of this slide, I mean, we're trying to conceptualize based on the data generated to conceptualize our cities into different layers in order to understand the cities into a better manner. So, as I mentioned, we produce huge amount of data every day, so we can say that we are in a big data era. So three main characteristics of big data usually categorized into volume, velocity, and variety, and it's consisted with both structured data and unstructured data. So what do I mean about the three kind of themes about the big data? So volume goes into the big data, the characteristic that data is so large, it cannot be stored into a traditional software anymore, which is Excel. And volume meaning, and also like all the data comes from a variety kind of sources that goes to the different kind of variety of the data coming from all the IoT sensors or the cross-source data. And the velocity, meaning that our data are developing so fast every day, so it's coming, rapidly produced in an everyday manner. And the data is associated with so-called the structure and the unstructured manner. So what would we have in terms of big data, right? We can say, well, I will go through this kind of very quickly because this is just a concept. But what we can say every day in our everyday lives, we can say that variety sensors contribute to our sensors, which collect the air quality or the building status data, right? And all these kind of sensors data eventually contributing to a concept of smart cities, which consist of huge amount of sensors every day in various places in the urban areas, and with the Internet of Things as backbones. But apart from the census data, we have crowdsourced data. And the crowdsourcing is usually refers to the practice of obtaining information by the volunteers. And with all those kind of informations, with geospatial information attached, we developed this concept of VGI, which is volunteered geographic information. And we've been using that actually back in 10 years ago, people already using the cross-sourcing data in order to analyze the urban kind of recovery after the nature disasters, such as the earthquakes showing on the paper in the left. But apart from the crowdsourcing data from everyday lives using our smartphones, we have big data from the sky, which everyone knows is the remote sensing data, right? And more recently, another source of data called Street View images is becoming more and more popular. For example, you can see that the university is actually on the left top of this slide, and also the various kind of Street View images are spreading across the world. And on the right top of the slide, I'm showing one of the crowdsourcing platform for the Street View imagery. It's called Maplery. It's all the data contributing to this platform are volunteered. So all the information, all the street views showing on this platform, everyone can use that for any purpose of research, basically. But it seems that all the data I just mentioned are geolocated, which is actually true. I would say that over 80% of data generated every day are georeferenced. So geographers use this kind of layered kind of a conceptualization of cities to analyze the city. And we, as urban planners or urban geographers, are joining our kind of little joins on the layers developed by the geographers or the GI scientist concept, GI scientist. But since we have huge amount of data, how do we actually handle that? Here actually comes the artificial intelligence, but I'm not saying the artificial intelligence is localized in any way, but we are developing towards to an AI era. But to have a brief kind of recap of AI has this kind of concept of AI actually developed ages ago. On the right page of this slides, there's this lady called Ada King, who was kind of first gave the concept of maybe the computers or the machines can be more intelligent. And through the past 50 years or 60 years, we see so many milestones papers developed about AI. For example, the Alan Turing in 1950 developed this kind of paper on the learning machines. And then we have so many concepts later on, which shows to be very important in the AI development, such as the multi-layer perceptions or the concept of deep learning. And nowadays, since 2007, when CUDA as was developed by NVIDIA, AI becoming more and more important, or is in a very process of like rapid development these days. And all these years, we developed all these kind of key models, such as in 2012, we have the AlexNet developed for the computer vision. And until in 2022, OpenAI released the ChatGPT, which everyone is using these days, right? But most of the studies in the past days are using AI technology to the spatial data in order to understand the city. This example is one of the papers that I developed when I was a postdoc in Finland. So in this kind of typical research, I developed this kind of deep learning based models in order to extract the location information from Twitter and then convert those information into coordinates so that I can finally map those kind of Twitter activities into a city, onto a city map. And all the kind of Twitter data we were trying to study was sports activities related kind of tweets. By mapping the sports related tweets using the deep learning method that I developed, I was able to uncover some hidden sports facilities that around the city, which people use those facilities for their everyday sport activities, but was not recorded in their official LIPAS sports facilities, which shown on the right part of this figure. Similarly, we see people using 3D view images, as I just mentioned, as a very important data source with computer vision technologies in order to uncover spatial spatial patterns in the city. We even see that people using street view images, which is on the right part of this figure, trying to through the street view images in order to understand the urban soundscapes. However, all the three research that I mentioned so far are using AI technologies into the on the spatial data. So they're sort of like bring AI to the spatial data, but AI here seems using as a tool. If we can all do that, just apply AI technology onto spatial data, then why we are not replaced by the computer scientists yet? I think, we have the sort of like, I have a brief answer here, is that I think our discipline is more than that. What we want to do is actually bring spatial into AI. So AI and spatial data can be mutually developed and interacted. So between jumping into this kind of concept, I think I need to talk a little bit about the concept in the AI, which is very important, is about prior. So how AI actually identify, for example, what is an apple, what is a pear, right? You have to sort of like tell the AI what is the apple. This kind of process of telling AI this is an apple so that AI can identify an image is an apple is called the process of injecting our human prose into the AI models. But what about geography prose that help us to develop cities? For example, we have the Tolber's first law of geography. We have spatial heterogeneity prose. Or even recently, we have a little bit like advanced but also controversial law prose of third law of geography. How do we actually inject, our understanding of the geographies, those kind of prose, into the AI development? And some geographers have give some of their answers already. They are trying to use the convolutional neural network in order to study the social demographic profiles across the whole England. As you can tell from the image here, so on the left part is a linear model. So they were trying to sort of like estimate the population in each cities across the whole England. On the left side of this image, they're using the linear model. And on the right part of this image, they're trying to use the convolutional neural network, which consists of this process as shown on this part. Well, let me annotate a little bit. So this part. So graph neural network essentially have this kind of filter trying to collect information across all the areas. It's scanning, right? And as you can see from the results, by using the convolutional neural network, the population that the model estimated seems to be more centered into big cities across England. For example, London, for example, well, I believe this is Manchester, and then this is Liverpool, and this is Newcastle. And all the population are centered into big cities, which is somewhat aligned with our underlying assumptions about how the population centered in the geographic areas. However, as I mentioned, however, sorry, I don't know how to let me clean this. Yeah. However, as I mentioned, we are in the big data era, and data is constructed with structured data and unstructured data. In terms of geography, structured data, meaning that data aligned like cell by cell or grid by grid, which you see for most remote sensing images, as you're probably aware of. But geography data often is unstructured, meaning that polygons with other polygons will be overlapped or intersected, or even one big polygons will contain another small polygons, right? Convolutional deep learning methods, such as the convolutional neural network I just mentioned, only deal with the structured data. But how do we actually handle the real-world unstructured geography data in our everyday lives for developing a better AI systems? My answer to this will be the graphs or the networks, as you are dealing in the past few days, probably. And from geography perspective, graph has long been used in our studies. We've been using the graphs to represent the transportation networks, to represent the street networks, to represent the space syntax or social networks. We're using the graphs to encode the geolocation proximities and also the distance. And very recently, there is this kind of new set of technologies called graph neural networks has been developed in order to better handle the graph data or the network data. And I'm not trying to, intimidate you about all the formulas that I put here, but I'm just trying to show that there are some famous graph neural networks in our discipline in order to handle the network data or the graphs. And all you need to know about the graph neural network is about message processing and the node information aggregation. Meaning that if we were trying to predict the information for the target of node A, we are trying to aggregate information from its neighbors, such as B and D, in order to help us to predict what is A represents for. And all this kind of information, for example, B will also aggregate the information from A and C will aggregate information from all its neighbors. And all the information aggregated on the neighborhood level will be sent into neural networks. And using these neural networks, we'll be able to identify what is A represents for. So we have, for the graph neural network, we have several kind of famous tasks, such as node classification, link prediction, graph classification, community detection, or element detections. Basically, all these kind of tasks will be formalized and help us to understand urban geography in a better way. So I'd like to talk about like a bit of my research. And as mentioned, how do we actually inject the geographic pros into the AI models? Is that we are trying to use the graph to model the first law of geography, but on the social networks. In this early research of mine, which was a study conducted during my PhD, I conceptualized all the geotweets locations as nodes as graph, and their spatial temporal distance between each other as various graphs. And I was trying to use a graph neural network on all the graphs that I developed or tested to classify what each their tweets represents for the human activities in the urban areas. This is one of the earliest work embracing the idea of spatially explicit GeoAI, meaning that we're trying to inject the geographic laws into the AI model. And we are thinking locations of social media beyond location itself, but a spatial temporal representation of everyday urban lives. This is one of the early research of mine into modeling the geospatial components of data using the graph neural network. Another typical research discipline in using the graph neural networks or the street networks is trying to understand the street networks. In this model, which I'm just skip this page, I'll come back later, but in this particular research, I conceptualize the street networks as the graphs in the city. And we have two different kind of tasks developed. First is that we're trying to use the street networks as the whole graph, meaning that we're conceptualizing the whole street as the network or the graph to be put into a neural network. And second one is we're still taking the street networks in the cities, but they're separated based on the administrative areas in Wuhan. So each kind of sub-administrative zone will have its unique street networks. We use these two networks to study two different questions. For the first one, we are trying to use this for the traffic analysis. We're trying to use the graph conceptualized of street networks to predict the traffic volume on each street in the city. For the second one, we're trying to predict the population volume within each administrative subgraphs. And by developing a graph neural network, we will be able to do that. But further than that, we will be able to add one additional component of expandable GeoAI, trying to explore why certain streets will have certain volume of traffic and why certain administrative zones will have certain volume of population. And if we alter the street networks inside each of the connections, will it change the traffic volume, or will it change the population volume in the city? For example, if you can say from the figure, if you can see from the figure on the right part, we're targeting on two kind of community areas inside Wuhan, and each of them have their street networks. And we identify what was the most contributing features of the urban features and the OSM connections contributing to certain volume of those two communities. By altering the connections of the street networks, we'll be able to increase the popular volume or decrease the popular volume so that we can provide sort of like preliminary indications for the urban planners if they want to increase or decrease the population inside the cities. And beyond the street networks, we've been using the graph neural networks and also the graph representations of the urban areas on the parcels, which is all the small areas inside the UK. In this study, we're using the spatial graph to represent all the urban areas. And we developed this so-called graph autoencoder in order to help us identify how the populations distributed across the whole London with their unique social demographic profiles. And we compared our model with all the traditional kind of models. We can say that by using our graph-based neural network, we will be able to identify the distribution of social demographic populations with more sort of like geographic perspective insights, so that they will have more sort of like geographic clusters that is more obvious distributed across the city area. And we're also using the graph representations on the buildings. In this particular research, we applied the graph neural networks with the buildings. So we construct the networks using buildings as node and its closeness to the surrounding buildings as edge. And by modeling the buildings into a graph, we apply the graph neural network on this specific building-oriented graphs for two different tasks, for the regression task and also for the classification tasks, so that we be able to fulfill the 3D geometric of the building informations. For example, for the regression task, we'll be able to predict the building height. We'll be able to predict the number of stories of one building. And for the classification task, we'll be able to predict the type of the building, or the materials, or even their ages. And we tested our model on three different kind of scenarios in three different cities, in Boston, Melbourne, and Helsinki. And we'll be able to identify that with the graph neural network and the building constructed graph, even with only 10% data available, we'll be able to produce reasonable predictions for the building information already. Another similar research also on the building-oriented graphs is on the LST, land surface temperatures. Still, we're using the building-oriented graphs and applying a graph neural network onto that, so that we'll be able to identify fine-grained LST patterns across the city. So each building in Singapore will have its unique local climate zone labels, which also verified by using the street view images in this study. And more on that is that this research I want to present is go beyond the urban areas, but we're using the networks or the graphs to conceptualize our outdoor activities. In this particular research, which is I'm also very proud for, because this was research I was done this when I was a postdoc in National University of Singapore. We're trying to conceptualize the human outdoor comfort as the spatial temporal interaction with each human's surrounding informations. So we built up these kind of 3D models of the National University of Singapore, and then we let participants to walk on a particular pedestrian path in the campus. And while the participant walking in the campus, we record several informations, including the noise, including the sound intensity, including the moment when they feel comfortable or not comfortable. While they provide their outdoor comfort, we also record their surrounding information using the GoPro, using the street view images. And we identify all the information from the street view images and conceptualize them into spatial temporal graphs shown on the downside of this image. And this means that, for example, when imagine you are actually walking outside, right? One moment from location A, you might say there's a cars and people walking towards you. But moment B, the cars probably passing by, but human will still be there, right? And moment 3, all the human and also cars are disappeared in your sight. And we're trying to conceptualize this kind of dynamic interaction of the surrounding urban elements into this kind of dynamic changing graphs. And we developed this neural network that stacked with a graph neural network with an LST network to model this kind of temporal dependence of the human comfort when they're actually walking outdoors. And we demonstrate that our model is achieved very good result. And this is just a showcase of how the model actually works and how do we actually, classify the human outdoor comfort. And furthermore, we are trying to develop this kind of interactive virtualization platform in the campus so that it can predict the human outdoor comfort in real time. by using our graph-based models. And go beyond the simple laws of geographies. If, for example, I mentioned about all those kind of geographic products in the beginning, right? Can we inject more than one geographic products or the knowledge into the AI model? This research is an answer to that. We're trying to combine two different kind of geography laws into one AI models. By developing a spatial-aware graphs, which is still based on the neighborhood or the proximities as graphs. But further than that, we're trying to develop a high-order relationship modeling, meaning that, traditionally, if two areas are close to each other, you combine them into one graph, into one line. Right? For example, if location A and location B are close to each other, location A and B will be conceptualized as nodes, and there will be a link between location A and B, right? But what do I mean about the high order relationship is that even location A and location D are far from each other. As long as they share certain similar urban characteristics, I put a link between them. So imagine you are in a city, right? And there are industrial areas which is far from each other. But given they're both industrial areas, they might share some similar kind of geographic underlying patterns. I'll put a link in between those two areas. And we use this kind of concatenated heterogeneous graph neural network in order to study the urban climate justice across London. And this is a recently published graph. We go beyond the street networks, but we also include the nature system of Singapore, the waterway connections. So we stack the street networks and urban waterway connections into one graph. And then we use this similar heterogeneous graph neural network in order to predict the land surface temperature and also the housing price in Singapore. And go beyond all the graph neural networks I mentioned, focusing on one scarce. Can we actually, using the graph representation of urban areas, to explore the scale effect of any geography phenomena? This particular research that I presented earlier in London was an answer to that, is that we're trying to use this kind of hierarchical graph neural network to model the hierarchical kind of patterns of the scale effect of the social demographic distribution patterns across London. So that we're using one graph neural network to produce 3 different classifications in one click. And we'll be able to use the graph neural network and to achieve this. And if you are thinking, after today's talk, you might want to explore the graph neural network, you might actually think, oh, this is probably too advanced, or this is probably too complicated, or too difficult. I would encourage to explore this because as Nabil just mentioned, that we met in Shanghai and we had this 1-week workshop on graph neural networks in urban analytics. And most of our students in the workshop had 0 experience of graph neural network, but they will be able to achieve some modeling using the graph neural network in just 7 days' time. I believe you can as well. And I would like to encourage you to explore more on that. So here are some of my 2 cents about my talk today. I think city models need to address and leverage a large number of different dimensions of knowledge based on the spatial knowledge I just mentioned, all kinds of spatial prowess or knowledge to be injected into AI models. And at a high level abstraction, these structures can be described as graphs with nodes. And we can use networks or the graphs in order to better conceptualize a city. And the spatial structures and geographic pros are key to be involved to develop the spatial explicit models to understand the urban governance process. And I believe the graph and network is fun. And I think there's still much to explore. And that's pretty much my talk today. I'm sorry, like if I'm going through everything too quick, but you are more than you're more than welcome to contact me and my email address so that you might want to study more on this topic. Thank you very much.
That was really great. That was really great. I don't think it was too much actually. In fact, I would say there was some moments of some buzz actually in the room. I think it echoed and corresponded with pretty much all the main topics we've been dealing with here the last few days, already 1.5 weeks actually. And I've just kind of boiled it down to keep it also comprehensive for you into two issues that really resonated in your presentation. Is it possible if we go to that slide again of England where you compare the shift from the normal graph to the neural graph? Yeah, this one exactly. Let me make this smaller. So this is, for me personally, kind of shocking because it suggests that our urban agglomeration is much more compact than we previously thought. Is that really true?
Yeah, well, this is actually, I think this is a great question. Maybe it's not, but this is an early research that developed back in 2019 when the neural network just becoming more and more popular, and people trying to use this kind of neural network in order to study the urban population across the whole England, right? And then they were trying to compare if the models of using the deep learning can give some, more spatially clustered representation of human distributions. So I wouldn't say this is exactly true. It might not actually be true, but it's just saying that by using this kind of deep learning technologies, such as the convolutional neural networks, it will be able to produce some of the phenomena that is more geographically clustered. Whether or not you want to use it is really depending on your modeling choices.
Yeah, like in my understanding, it is certainly much more realistic to adhere your first law of geography, right? Where there is a sort of a glue, a spatial glue between each entity, if it's a human or a building, which would mean that this kind of level distribution within a geographic zone on the left here is not accurate. So in that sense, I'm convinced the neural network does a much better job. But what we are kind of also facing is at the same time the neural network introduces a new bias, and that's kind of something we are really not quite ready to kind of wrap our heads around.
Yes, that's true. That's very true. So that's why I think, if you're looking at another research that I presented, is in this particular research, I'm not only developing a prediction model, right? But I'm also trying to use explainer model, trying to explain the predictions so that we understand which would be the dominating features. So model makes certain predictions, and then we can unpack those kind of predictions or the features. So we alter the features. Will the prediction change or not? So we'll be able to sort of like interact with the AI models in a more intuitive way, I think.
That's very interesting. That's very similar to at least what we've been thinking about, not so much doing yet, but overlaying different sets of data. So on the one hand, the graph, which is a linear structure, but then kind of superimpose, if I understand this image correctly, with a spatial a surface area, and having those interact or at least kind of compare to each other. Is that's how I can understand this image, right?
You can, yes.
So that's very interesting. That's also what we've been discussing. One of the big topics that arose is what makes you decide for a certain number of data points, or the type of data that you're going to analyze in order to do this type of overlap, because your options are quite broad, right? It's
Yes.
almost more like whatever is available, which is
Yes.
also a biased.
Yes. That is also true, but I'd like to also briefly say something more about one research, which is, I think, I think this one. So this is about the geodemographic classification, right? In geodemographic classification in the UK, they usually do this once every 10 years. And then it's involving a huge process of filtering the data which are suitable for the geodemographic classification, which is, in the traditional method way, right? But in this model, we just input all the data into graph neural network, and it's produced almost a similar kind of result compared to the traditional method. So it's kind of like help us to skip the tedious or even and also lengthy kind of process of manually selecting variables. I think that's also something, neural networks stand out because its ability to identify the non-linearity that inside the data, it helps us to skip those kind of data selection process, I would say.
Right. That's super interesting. Based on parcels, but then and so what kind of dimensions are we looking at here? Is it
Dimensions.
as in, are these still defined by districts or by pixels, or is there like a spatial?
No, there are small areas in the UK. So in England, they have these kind of small areas called output areas. Each of the output areas basically have, the idea of output areas is like output areas will roughly have an equal number of populations distributed in the areas.
Uh-huh.
And they were derived from the administrative areas and then, further derived into each parcel. So
Oh,
they're just each polygons.
that's super interesting, but that's a luxury that you have to have. Maybe Northern
That's true.
Europe has that. We certainly don't here in Indonesia.
Yeah.
So we're also kind of dealing with this kind of dirty reality. How do you navigate that type of decision-making process? How you set up your model, etc. Based on the sheer fact that your available data is quite limited.
Yeah. That would be an issue actually, especially for AI development because you need to have data.
Yeah. Yeah, although I am excited about that the graph, especially in the beginning of your presentation, the graph itself is already very valuable and tells you a lot
Yeah.
already.
Yeah. Exactly.
And that we have, right?
Yeah. Yeah.
And we're kind of slowly tagging additional attributes to the graph where if and where we can, and failing at the same time.
Yeah.
It's been super fascinating. Allow me to do something rather cheeky.
Yeah.
If we have some specific questions, can we kind of loop back to you over the next few days, maybe, and
Sure.
send an email? And
Yeah.
then okay. If there's any other specific questions, otherwise I don't want to keep the rest of it any longer. Anybody have any specific questions in addition to those three questions? I put way too much pressure on them. I don't think that's going to result yield any new questions. In that case, warm applause. Thank you.
Thank you.
You're on mute, but it's rather excited. It's really inspiring. It's really inspiring.
Thank you very much.
And it's like you suggested, it does give us that little push that we needed.
Okay.
We talk soon, yeah?
Yeah. Thank you very much. See
Thank
you.
you. Bye-bye.
See you.
Bye-bye.
Bye.